Hi, welcome to the Euclidean Geometry 101 course, part 4 in the chapter about triangles. We will now show some propositions that are valid in every triangle. In lesson 6, where we introduced polygons, we defined an exterior angle to a polygon. Applying this to triangles, we can now state proposition 10. An exterior angle of a triangle is greater than any non-adjacent interior angle. We need to prove that in the triangle ABC, the exterior angle DAC is greater than the angle ACB and the angle ABC. So first we try to prove that DAC is greater than ACB. We connect B with the midpoint E of AC. After this, we extend BE with EF, where EF is equal in length to BE. Then draw AF. Now, AF lies inside of the angle DAC. So that means that angle FAE is smaller than angle DAC. Let's consider the two triangles BEC and FEA. You can see that they are congruent triangles, like a SAS congruency case. And that because the angles in E are opposite angles, BE is equal to EF by construction, and EA is equal to EC, as E is the midpoint of AC. So, angle BCA is equal to angle FAE, as another angle of these congruent triangles. But we already knew that angle FAE was smaller than DAC, so angle BCA is smaller than DAC, and therefore ACB, which is the same angle, is also smaller than DAC. Now, on to the second part of this proof. We need to show that angle DAC is greater than angle ABC. We follow an analogous reasoning. We connect point C with point E prime, the midpoint of AB. Then we extend CE prime with E prime F prime, which is equal in length to CE prime. Finally, we draw F prime A. F prime A lies inside of the angle D prime AB, so F prime A E prime is smaller than the angle D prime AB. Consider the triangles B E prime C and F prime E prime A. We can conclude in the same way that they are a side angle side congruency case. The angles in E prime are opposite angles. BE prime is equal to E prime A because E is the midpoint on BA, and CE prime is equal to E prime F prime because we constructed it that way. So that means that all other parts of those triangles are also equal 2 by 2, and more specifically, the angle F prime A E prime is equal to the angle ABC. Combining this with the comparison to D prime AB, we have that D prime AB is greater than ABC. But we needed to show that DAC is greater than ABC. Since DAC and D prime AB are opposite angles, they are the same, and so the proposition is proven. This proposition can also be stated in another interesting manner. The sum of two angles of a triangle is smaller than a straight angle. Let's look again at the figure. We have angle DAC is greater than angle C, and angle DAC is greater than angle B. On the other hand, we know that the angle DAC and the angle in A are supplementary angles. So DAC plus A equals 2 right angles. And so C plus A is smaller than 2 right angles, and B plus A is also smaller than 2 right angles. Now that we are on a roll, on to proposition 11. In a triangle, we have opposite a greater side a greater angle. Let's consider the triangle ABC, where BC is greater than AC. We have to prove that angle BAC is greater than angle ABC. In other words, the angle in A is bigger than the angle in B. Let's take on CB a segment CD that's equal to CA. Draw DA. The resulting triangle ADC is isosceles. In this triangle, the angle M is equal to N. We know that N is smaller than the angle BAC because D lies between C and B. So M is also smaller than BAC. In relation to the triangle ABD, M is an exterior angle. We know that an exterior angle of a triangle is greater than every non-adjacent interior angle. So angle M is greater than angle ABC. And we already had that angle BAC is greater than angle M. We can thus conclude that angle BAC must be bigger than angle ABC. What needed to be proven? We can also state the converse of this proposition. In a triangle, opposite a greater angle, we have a greater side. We show this in triangle ABC. In this triangle, angle A is bigger than angle B. We need to prove that the side BC is bigger than the side AC. First of all, if side BC is equal to AC, then the triangle is isosceles, and we know from proposition 6 that the angle B is equal to angle A in that case. Let's assume that side BC is smaller than AC. The direct proposition shows us that angle A must be smaller than angle B. But this contradicts what was given at the start. So BC must be greater than AC. That's it for this lesson. Next lesson, we will talk about sum of sides in a triangle. If you like this series, consider subscribing to my channel.